microscopic levels of distances, 100 microns to create another excitation. And this way you sort of create your phase gates. Now, why does this happen? It's because of the fact that the Rydberg interaction with the molecule shifts. If you have a rotational molecule, will shift the rotational levels. I described it to you. This interaction, for instance, between the electric field of the Rydberg electron and the dipole moment of the polar molecule, which is like this. It's like 1/r², electron-dipole interaction. For typical rotational splitting of about 1 gigahertz for KRB, for instance, then we would shift the rotational levels of KRB as a function of R like this. So this is, for instance, J equal to 0 level, J equal to 1, 2, and 3. And you can see that at separations of these molecules over here, at about 1,000 Bohr radii or so, there's the shift is very large, in the order of 30 megahertz. Meaning that if you, for instance, have your Rydberg atom, this is the Rydberg atom structure, is the molecule, J equals 0, the 0, 1 states are from J to J plus 1. Then, if you make a Rydberg excitation here, in this system, from the ground to Rydberg, then this interaction shifts the rotational levels of this molecule, this way. And then, if you tune to this shifted resonance, then you can do your gate operation, separated from all other molecules, just on that molecule itself. And you can do another one, another one, another one, because of this shift. This is in a rotational molecule. You can do the same thing actually also you can do the encoding in a hyperfine state, in a lambda-doublet molecule, as I mentioned. So this is an example of a lambda-doublet molecule. This turns out to be CH in a metastable state. Okay, I'm not going to go into the details of why we chose metastable, but just for convenience. Nevertheless, I mean, when I say metastable, this CH metastable lives for about 1,000 seconds. Remember, in lambda-doublet, I said it's not a rotational molecule. In other words, the rotational splitting between J equal to 1/2 and 3/2 is about 500 gigahertz, very large. However, the molecule can be polarized by overcoming these two opposite parity states, the E and F states, or over here, actually, for metastable between E and F states. This splitting is about 700 megahertz, and the dipole moment is about 1.45. In order to do hyperfine encoding, and this is not something we do, but this is something that typically is done, including in Professor Junier's group for OH, is to look for transitions which are insensitive to the magnetic field. So that in the range of magnetic field which the trap is operating, if hyperfine levels are almost immune. This turns out to be, for instance, for CH, between for these states here, this one and that one. In this range of about 2.4 Gauss, they're very insensitive to magnetic field, and then you can calculate the energy splitting between these two opposite parity states, F and E states, and it turns out to be this splitting is about, for the E state, the hyperfine splitting for the E state would be this, and for the F state would be this. It would be minus 21 megahertz, in this case about 2.6 gigahertz. These calculations actually were done for us by very talented postdoc Timur Sherwood at ITAMP. Yes, so you can actually then also encode into hyperfine levels in lambda doublets, and these actually have very large coherence times. Now, what we are proposing is to make marker atoms of Rydberg atoms for qubit coding. Next week, Professor Marcus Grinder will give you overview, details of their really amazing experiments where they can actually image atoms in an optical lattice, the so-called atom microscope. You will be here, I think, next week. What we sort of, in a sort of a parody, if you wish, we're calling ours a molecular microscope. These marker atoms actually have been proposed by Tommaso Calarco and Peter Zoller and others a few years ago, in which you take atoms in an optical lattice, okay, and another set of atoms in, let's say, another optical lattice overlaid on top of it, and then you mark this interaction by collision between this marker atom and the atoms, let's say, R sub I in this optical lattice. And this is done, and this is the way that you could encode the cube. It turns out this is done by collision, so-called state-dependent selective collision induced qubit shift. So they shift the atomic lines here by collision. Collisions, unfortunately, or maybe fortunately, lead to spin flip. So you can actually lose your atoms from the trap when you have collisions. Over here, what we're doing, we're inducing these shifts, not by collision, but by interaction. There's no collision involved. Therefore, we think is that ours should be a more robust way of marking these polar molecules now, these not atoms, but polar molecules, to create these systems that I just described. All the details are in this paper, which appeared in PCCP, a special issue, Physical Chemistry, Chemical Physics, because I think it was not obvious yesterday, of this journal maybe. And I think with that, I stop.
Thank you, Hossein. Questions or comments?